Welcome back to the second video in this series of videos on motion. Now at the end of the first video I assigned homework in the form of this problem where you were given an object that was initially moving at 4 meters per second. Obviously it had been accelerated to that speed prior to observing this system. So we start off in our observation of the system with the velocity as 4 meters per second in the easterly direction, and after a period of 8 seconds the velocity is now 28 meters per second. You are asked to sketch the velocity versus time graph, then to determine the acceleration, and the assumption here is that the acceleration is uniform. We are looking at a consistent net force accelerating the system. There isn't a sudden change in the net force resulting in something called jerk. We are dealing with, in these problems, with acceleration values that are constant. Then you are asked to sketch the change in position versus time graph, also referred to as the displacement versus time graph. You were asked then to determine the total displacement after 5 seconds. And then lastly, you were asked to sketch the acceleration versus time graph. We are now going to look at the solutions to these problems. In sketching the velocity versus time graph, we sketch the t-axis in seconds and we label it. We need to cover a time interval of 8 seconds, so we label the t-axis such that we fit in 8 equal increments of time. Then the final velocity after 8 seconds is 28 meters per second, so I decided to use a scale of 1 increment on my vertical axis, which is the velocity axis, to represent 1 increment to represent 4 meters per second. So it goes 4, 8, 12, 16, 20, 24, and keeping it constant at that scale. It's very, very important that one keeps a constant or consistent scale on a particular axis. If we view each of these increments as 1 centimeter, then on this scale, the scale is 1 centimeter represents 1 second. If we view each increment here as 1 centimeter, then on this axis the scale is 1 centimeter represents 4 meters per second, and one doesn't change that scale. That is really very, very important. This is quite an easy graph for us to sketch because we know that the initial velocity at t equals 0 seconds was 4 meters per second, and that after 8 seconds the final velocity was 28 meters per second. We can draw a straight line because of the fact that this system is accelerating uniformly. In other words, the acceleration is constant. Now, if we look at the second question asks us to use the graph to determine the gradient. So the acceleration is the gradient, and acceleration by definition is rise over run. The run being the change in time, in other words the time interval, and the rise would be the change in the velocity. So this is rise and this is run. So using rise over run as change in velocity over change in time, the change in velocity over the 0 to 8 second interval is from 4 to 28 meters per second. So v final minus v initial is 28 minus 4 meters per second. And the run is the 8 seconds. This gives us 3 meters per second squared. The plus sign indicates, according to our sign convention, that the acceleration is in the easterly direction. In question 3, you are asked to sketch the displacement versus time graph, or the change in position versus time graph. Now, this is not an easy question, and it's quite time consuming if we do it in the manner that we're going to do it for the time being. So we're going to use the fact that the area under a velocity versus time graph is the change in position. Now, in this particular system, the object is accelerating at 3 meters per second squared for 8 seconds up to a velocity of 28 meters per second. The fact that it's uniform acceleration means that every second the velocity changes by plus 3 meters per second. Therefore, we get a straight line. Now, for this particular problem, we actually need to be able to work with the areas under the graph successively for each second being added to the motion. So for the first second, we need to work out the area under this part of the graph. Then, to work out the change in position of the object after 2 seconds, we need to work with the area under this section of the graph. And to work out the change in position after 3 seconds, we would need to work out the area under the graph and of this part of the graph. Now, that means that we need each of those points for each of these time values. So if you start with 4 meters per second, after 1 second, the velocity increases by 3 meters per second to 7 meters per second. In the next second, the velocity is going to increase by another 3 meters per second to 10 meters per second. And the same will be true as we move along here. Between each of these points, the velocity is going to increase by 3 meters per second because the time is increasing by 1 second. And the acceleration is 3 meters per second per second. Once you have done that, then one can start to work out the individual areas. So starting off with the area under the graph for the first second, between 0 seconds and 1 second, we find that we are confronted with an area of a trapezium rather than the area of a triangle, as in the example that was shown in the first video. So the area of a trapezium is a little bit more complicated. You can think of it as the area of a rectangle plus a triangle. But because we've got to do a lot of these calculations, it's better for us to rather use the standard formula for the area of a trapezium. And that is that the area of a trapezium is equal to the average of the two sides. So we get the average by taking the one side and the other side and then dividing by 2. And if you do that, then in actual fact what you're doing, this would now be the average height. I'm going to use h bar, and this would be h bar. And you can see that in effect it works out to being a rectangle with the same area as the trapezium. You can think of that little area there as flipping over into that space. And then it just becomes base times perpendicular height, and b times height gives us x plus y over 2 times the base. So we're going to use this formula throughout this problem to calculate the areas under the graph. So for the first area, we have that the base is 1 second, the heights are 4 meters per second on the left hand side and 7 meters per second on the right hand side of this area. So 4 plus 7 divided by 2 gives us the average height, which is 5.5, because 4 plus 7 is 11 divided by 2 is 5.5, times 1 is 5.5 meters. It's a positive area, which means that this change in position is east. Now, using this method, we are now going to calculate the areas under the graph going from 1 second to 8 seconds. And we're going to go through this pretty quickly. So keep in mind that we are going to continually work with the total change in position from 0 seconds to a particular point in time. So all of these values are going to be the distances or the displacements of the object from where it originally was when we started observing it. So between 0 seconds and 2 seconds, the area under the graph would be a trapezium with sides 4 meters per second at 0 seconds and 10 meters per second at 2 seconds. So substituting the 4 and the 10 into the heights of the trapezium, dividing by 2, adding them together and dividing by 2, and then multiplying by the base. So the base has gone from 1 second now to 2 seconds, and that gives us a change in position of 14 meters from the original position at 0 seconds to where the object is at 2 seconds. Doing this successively for 3 seconds, 4 seconds, we get increasingly larger changes in position from where the object originally was. This makes sense. It should make sense because the object is moving further to the east every second because it's moving in the easterly direction. So therefore, its displacement from where it started should be bigger, and the areas under the graph should successively get bigger and bigger. These are the calculations for the change in position at 5 seconds, at 6 seconds, at 7 seconds, and my advice to you is that if you didn't get these right, that you pause the video now and you do these calculations for yourself, because it's really important that you are able to do this, because you're going to get another problem like this at the end of this video where you're going to have to apply this method again. So now we've managed to calculate the total change in position of the object up to 7 seconds. Lastly, we now get to 8 seconds, and here we work with a base of 8 seconds. The initial height, the initial velocity was 4 meters per second. After 8 seconds, it's now 28 meters per second. Using the area formula of a trapezium, we work out that this is 128 meters. Now that we have all these values, we can now look at sketching the total change in position versus time graph for this object's motion. I have set up a table here of all the values that we've calculated. These are the values in black are the values we calculated previously using the area of the trapezium for each of the time intervals. And now plotting the total change in position versus time, I use a time axis which is able to have 8 intervals of time, 1 second each on its horizontal or time axis. When determining what your scale needs to be for the vertical axis is the change in position, one needs to look at what is the maximum value that you need to be able to represent. And so I worked with 10 meters per 1 centimeter interval, and I used 13 centimeters to be able to accommodate 128 meters. Once I'd done that, I plotted each of these points on here. So for instance, 1 second is 5,5 meters. At 2 seconds, the change in position was 14 meters. So this point would represent 2 seconds, 14 meters. For instance, this point here at 6 seconds would have an associated change in position of 78 meters, which is just under 80 meters. And so plotting all of this data, we get data that looks like this. Now, one must be careful here because one can be very easily tempted to draw a straight line through this data like that. And that would be a very inaccurate fitting of the data because, as you can see, it doesn't really fit the data that well. There will be points that are very, very, very far off a line of best fit. So it is better to use a curve of best fit, and this curve, as you will soon see, is in actual fact a parabola. Question number 4 asked us to work out the total displacement. Well, we've already done that, but I would like to revise it because this is something really important comes out of this. Looking at the velocity versus time graph, very simply, we had a time axis and we had a velocity axis. We had an 8-second interval, delta t equaling 8 seconds along the horizontal axis. Initially, VI, the initial velocity, was 4 meters per second. At 8 seconds, it was 28 meters per second because the final velocity, VF, was 28 meters per second. Because the acceleration is uniform and the acceleration is the gradient is uniform. In other words, the graph is a straight line, and that's because straight lines have a consistent gradient. Now, the total displacement is equal to the area under the graph, as we've already discussed and used extensively. So writing this in a general form, this would be the length of the left-hand side of the trapezium plus the length of the right-hand side of the trapezium, or should I rather say the height, the left-hand height and the right-hand height, divided by 2 to give the average height. The average height would be approximately there, right, times by the time interval, delta t, and this gave us 128 meters, and it was in an easterly direction. Why I have revisited this is because this particular equation is one of the standard equations of kinematics that we'll be using shortly to solve numerical problems in kinematics. Lastly, you were asked to draw the acceleration versus time graph. Now, I've used the term draw, but in actual fact, when we talk about drawing, we often refer to a scale drawing. We're referring to a graph where we would have very specific values on our axes. So we'd be working according to a scale. But it's actually probably more accurate to use the term sketching. This is a sketch graph because you can see I haven't used a scale here on the vertical and the horizontal axis. I have put in significant values on each of the axes. I have labeled them, which is always important to do. But the acceleration is 3 meters per second squared, and it's a constant value. So over the 8 seconds, the acceleration never changed. It was 3 meters per second squared. Now, I'm going to say it again. The acceleration didn't change, but that doesn't mean that the velocity didn't change. The velocity was continually changing at a rate of 3 meters per second. So the acceleration versus time graph is actually a horizontal graph, straight line graph. It's actually a very simple graph. And that is why I was confident enough to give it to you, even though we hadn't done it in the previous video. So thus far, we have encountered 2 standard equations of kinematics, which have come out of the graphs of motion that we have covered. So let's just revise what we've done thus far pertaining to equations of motion. So if we have a system where an object with an initial velocity, vi, is being accelerated at a uniform acceleration to a final velocity vf over a certain time interval delta t, and resulting in a change in position delta x, then the following equations can be derived from the velocity versus time graphs. So the acceleration is the gradient of a velocity versus time graph, and if one rearranges this equation, one gets this equation. And if one works with the area under the velocity versus time graph, as we have just done in the homework, then we land up with this kinematic equation. And we will be using these two equations shortly. So the homework I would like to assign you is the following problem. There is a motor car that is traveling at an initial velocity of 30 meters per second. It then decelerates by applying brakes to a standstill where it comes to rest at 0 meters per second after 6 seconds. Now, when we refer to the term deceleration, deceleration is in actual fact just a negative acceleration, as you will see when you do the problem. We will discuss deceleration in more detail in the next video. But for the homework, I would like you to sketch velocity versus time graph for this particular system, determine the acceleration using the graph, in other words using the gradient of the graph, then sketching the change in position versus time graph using the area under the graph, and then sketching the acceleration versus the time graph. Prepare yourself for the fact that these graphs are going to look slightly different to the graphs we have done in the two previous examples. So please do this, and in the next video we will look at the solution to this problem, and then we'll delve deeper into equations of motion.